Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are starting our first lecture in week 7. We have studied until now crystal structures, different types of structures, and differentiation between crystalline and non-crystalline materials. We have also learned that properties of materials are greatly influenced by their structure. Actually, property depend upon the structure. We further learned that not all materials are perfect, that is, inherently by default, internal arrangement of constituents is not perfect, and this creates what is called defects in solids. This is referred to as imperfections in solids, and that a material that otherwise must be or could be perfect means the arrangement is totally perfect. This misarrangement or lacking of continuity in arrangement or presence of some other external element in the arrangement is referred to as imperfections or defects in solids. In next couple of lectures, we will be learning what is meant by imperfections, what are their different types, and the role they play in affecting the behavior of materials or giving materials the properties that they do have, what is the role of these defects or imperfections. You will learn that actually sometimes we do create defects to attain some desired characteristics or properties from that particular material. Okay, in this week, as I said earlier, we will be learning different types of defects. In this week, we will talk more about vacancy and self-interstitial defects. Vacancy or interstitial defects. Interstitial defects will be of two types: self-interstitial or foreign element getting into the interstitiations in the materials. Then we will learn to calculate number of vacancies at a given temperature. Then what are the solid solutions, weight percent and atom percent calculations of the compositions or concentrations of different elements in an alloy. Then another type of defect, that's called linear defects, dislocation and their types, and then grain boundary and twin boundary defects. We will learn to calculate vacancies theoretically by a formula. Moving on to our first type of defects. Before actually talking about particular defects, let us define what the imperfections or defects are. As we said earlier, all the solids, actually every solid, do not have a perfect crystalline or regular arrangement of atoms or constituents. Crystalline materials are which have regular arrangement of atoms or unit cells or constituents. This regular arrangement, however, is not perfect. There is actually no perfect order present in almost every crystalline material on an atomic scale. All the materials, therefore, have large number of various types of defects or foreign elements or external elements. These defects or external elements are called imperfections because their presence actually disrupts or otherwise disrupts the material that is otherwise supposed to be a perfect crystalline structure. And of course, we refer to crystallinity as the long range order of the unit cells. So when this long range order is disturbed, this disturbance is given the name of imperfection or defect. These defects are imperfections, they are the same word, same thing. With these create deviation from crystalline perfection and they affect to a larger extent on the properties of materials. As you know, sometimes we intentionally add or produce these defects to our own interest. You have very famous example of creating N-type and P-type semiconductors. There you bring in foreign elements into a particular host material to improve its certain electrical properties. So defects are not always bad as the name suggests, or imperfections are not always as bad as the name suggests. Sometimes you do create these defects and imperfections to our own needs. Just like I gave you an example of doping of an element to create extrinsic semiconductors, and another where you add, for example, carbon into iron for enhancement of mechanical properties or mechanical characteristics, and we get a product that is more mechanically better or improved than the original constituents or individual constituents. We therefore refer to crystalline defect as a lattice irregularity with one or more of its dimensions on the order of an atomic diameter. Okay, so defect or imperfection is defined as a lattice irregularity with one or more of its dimensions on the order of an atomic diameter. These crystalline defects or imperfections are classified according to the geometry or dimensionality of the defect as we have defined defects. So in the light of the definition, we have divided these defects into different categories. Prominent defects that we will also be talking about in next include point defects, linear defects, interfacial defects, bulk or volume defects, and atomic vibrations. These atomic vibrations actually are also taken as a defect or imperfection in the system. We will talk about it very briefly. Each of these defects we will be studying in next couple of slides one by one. We start with point defects. Point defects. These defects are associated with one or two atomic positions, as the name suggests, pointed at a particular position. So these defects are associated with one or two atomic positions. The simplest of point defects is vacancy or vacant lattice site that is otherwise occupied. You can see in the figure where on the right you are shown a defect, that is vacancy defect, and on the left you are shown a defect, that is self-interstitial defect. I hope you can easily understand the type of these defects seeing these figures on left and right on your slide. The presence of vacancies increases randomness of the crystal, that is its entropy, because this is an disorder. So disorder simply increases entropy. Equilibrium number of vacancies depends on and increases with temperature according to the relations given in 4.1 on your slide. as you increase the temperature, number of vacancies will increase. In this relation, N is total number of atomic size per cubic meter. QV is the energy required for the formation of a vacancy for a particular material or an alloy, and that is given in joules per mole or electron volts per atom. T is absolute temperature in Kelvin, and K is the gas constant or Boltzmann constant. Okay, on the other hand, interstitial is an atom present in the interstitial site or position that normally is unoccupied. Okay, this interstitial means the space generated because of the placement of atoms along near one another. Just like you see in the unit cell formation, and we were talking about the atomic structure, you see in BCC and FCC and the SCP, the vacant spaces created when the atoms come closer together and touch each other. The spaces in between, these are called interstitials or interstitial position. Interstitial is then interstitial atom or vacant or defect is an atom present in the interstitial site or position that normally is unoccupied. Okay, so vacancy is actually absence of an atom from a position that is normally occupied, and interstitial is presence of an atom in a position that is normally unoccupied. Like for example, in figure 4.1 in your slide on the left side, an atom present at a position that otherwise must be unoccupied or remain unoccupied, and that atom is from same material from within. So that is called self-interstitial because it is from the same material. It just change in temperature gave it vibration or jerk, and it was displaced and went into the interstitial position. Self-interstitial is then an atom from the crystal that is crowded into an interstitial site. A small void interstitial is a small void space that normally is unoccupied, as shown in the picture. What actually is a basic requirement for an atom to get into the interstitial position? What are 2-3 required or favorable factors that will help an atom to get into the interstitial position? If for example, the diameter of an atom is higher than the interstitious space, can this atom go into the interstitial position? Of course, it will depend upon the difference in diameter and the space. If that diameter of the atom is very big, of course it cannot go easily into the interstitial position. If diameter is somehow comparable and there is an external factor like temperature, like energy, that helps to get into the interstitial position, then an atom with comparable diameter or a bit smaller or a little bigger diameter will get easily into the interstitial position. Of course, the more comparable the diameter is, the more easily it can go, and little bit bigger diameter, it will go with provision of external energies like increase in temperatures, and then this interstitial of course will increase the stresses around its on the atoms that are in its surroundings because of its bit higher diameter. Okay, we move on to the next, and we see, just like we talked about earlier in the previous slide, self-interstitial is an atom from the crystal that is crowded into an interstitial site, a small void space that under ordinary circumstances is unoccupied, as we have seen in the previous figure 4.1. Now figure 4.2 shows us substitutional impurity atom that has substituted and has taken into vacant site an interstitial impurity atom that is small enough to get into interstitial site. Okay, there was a vacancy that was generated as we saw in the previous slide here on the right side, and then a self-interstitial atom from the same material goes into the interstitial position. Now here it is, there is a vacancy, and then into this vacancy an external atom has come in, an impurity atom, a foreign atom, or an atom that we have maybe intentionally added, and that has went into this vacant position. So we will say this has substituted an atom or the host atom that must have or otherwise must be present in the position. So that is will be called substitutional impurity atom or substitutional defect, substitutional vacancy. And then if you can see right in the corner or left bottom corner of your figure 4.2, there is a external interstitial atom into the interstitial position, and that you can see by yourself that it's very small in comparison to the atoms in the surroundings in diameter, and it is small enough, this small diameter actually allows it or facilitates it to get into this interstitial position. So another type point defect is called substitutional impurity atom, and that has substituted the host atom and its position. Here the external atom has got into a position that is vacant because of absence of parent or host atom in the structure. These defects will cause strains in their surroundings in the crystalline structure depending upon their size and position. Okay? Self-interstitial will produce relatively large distortions because in its surroundings, as it gets into a position which is smaller than atom itself, so it will actually bruise into or strongly get into intrude into the structure, so it will create larger stresses or strains. Anyhow, the formation of this type of substitutional foreign interstitial atom getting into the interstitial position is quite less in probability. You can understand because it needs larger energy and comparable diameter to get into the interstitial position. So normally this defect is very less in comparison to this substitutional or self vacancies impurity atoms that get into the vacant sites. So the chance of substitutional defects is very less in comparison to the vacancy defects. Going on, as we have said earlier, when all materials are perfect, not all materials are perfect. Actually, on the order of 10 raised 22 to 23 impurity atoms are present in 1 cubic meter of a material that is 99.9999% pure. So you can see for yourself that there is quite a good amount of impurity atoms that are, you can say, by default present in the material that actually is referred to as pure material with 99 plus percentage of purity. Still in this material there is a huge amount of impurity atoms. Sometimes we intentionally add foreign atoms or impurity atoms into the host lattice. However, on the order of that of your type 20, 10 raised 22 to 10 raised 23 impurity atoms are present in 1 cubic meter of material that is otherwise 99.9999% pure. We add impurity atoms. Why do we add impurity atoms? There must be different reasons. This depends upon our desired material, our material with our desired characteristics or properties. So we add impurity atoms to obtain an alloy with specific characteristics. That is semiconductor material that we obtain, then steel products that we obtain. We are adding intentionally the foreign atoms or another material into the host material. Okay, when we add impurity atoms to a metal, it results in the formation of a solid solution. Okay, that is, the host totally incorporates the foreign atoms into its crystal structure, and that is called the formation of a solid solution. That when you bring in an external metal or element into an host metal as an element, and that is just absorbed or dissolved in the or incorporated in the host metal or atoms, then they are thought to form a solid solution. Of course, this will be a single phase solid solution, but there could be another phase that appears in the solid solution, and that actually is physical appearance, physical difference. Otherwise, solid solution actually is a solution in which the crystal structure, the host crystal structure or the original crystal structure is maintained. So this second phase is actually difference in physical appearance that appears in the solid solution, and that we can recognize looking at the solid solutions. How this second phase appears? If we continue addition of impurity atoms into the host atoms, that at one time may result in a second phase appearing depending upon the kinds of impurity, their concentrations, and the temperature of the alloy. For example, you add sugar in water, which is initially absorbed by water, and you cannot see, sugar traces present in the water. If you continue addition of sugar, it will continue getting absorbed or dissolved in the host, that is water, but a stage will come when you will see sugar start appearing, actually residing in the bottom of the glass of water, and that is the physical appearance of sugar, and that is called another or separate or second phase. And of course, if you increase the temperature, then you are able to add more sugar and than before in comparison to the sugar amount of sugar that you added at the earlier temperature. Of course, and then at increased temperature, the second phase will appear with a greater amount of sugar absorbed or dissolved in the host material. Okay, so if we define solid solutions, the constituents a solid solution, a solvent or host element that is present in greater amounts, that is called solvent, or host that actually takes in the external elements or metal or material. The solute is element present in the minor concentrations, that is the foreign element or the doped element is called solute, and that is it in smaller concentrations. That these are the two major components of a solid solution. See, that solid, you can refer that this solid solution is actually formed because of defects that you have generated by yourself. You have brought in second or external atoms into another host atom that was before this addition, you can say pure, and with, of course, with the naturally present impurity atoms. So this solid solution is also a solution that contains defects in the sense that in its original basic or host atomic structure we have presence of another atoms that were not actually present in the host crystalline structure before addition of this foreign or second or solute atoms into the solvent. Okay, how solid solution is formed and what is that solid solution we have defined earlier. A solid solution is formed when solute atoms are added into the host but maintaining the original crystal structure, and we do not get any new crystal structures formed. Solid solution is compositionally homogeneous. Solid solutions are of two main types: substitutional solid solution and interstitial solid solutions. I leave this up to you to define by yourself what are substitutional or interstitial solid solutions. I hope you can simply understand by the very name of these types of solid solutions that what is a substitutional and what is a interstitial solid solution. Okay, then what are the factors that determine solubility of solute in solvent? I mean, what are the factors that affect addition or solubility of external element or atoms into the host atom or element? There are four factors, and that are atomic size, crystal structure, electronegativity, and valence. Of course, if there is less difference in atomic structure, atomic radii, atomic size between the two atoms, I mean less than 15%, there will be more addition of solute possible into the solvent, and no new phases will be formed. If, however, the atomic radius has a big difference, you cannot add more of the solute into the solvent, and there will be greater stresses generated or distortions created because of this external atom or solute that we talked earlier when we were looking at the figures. If the second is crystal structure, of course, if the crystal structures are similar, there will be greater solubility of the solute into the solvent. Electronegativity. If one element is electropositive and one electronegative, they form intermetallic compounds. Otherwise, they form substitutional solid solutions. And the valency, a metal will dissolve easily another metal of higher valency than of a lower valence. These are the four factors that affect formation of solid solutions. Here we just finish our first lecture, and we see each other in the next class. Thank you. Assalamu alaikum.